balance against that P term. So there's the original equation, Q times C plus P, so you can arrange in a whole lot of ways. A lot of times you're solving for Q, because you mean what P? The P term is always proportional to feeding rate. So when we're designing these systems, we go, okay, at maximum loading, what is our feed rate? Once we have our feed rate, then we have the production term, which is all the ammonia and the carbon dioxide and the oxygen and the solid, as Bert showed in your slide. Very nice slides, Bert. Particularly the videos are really good. So you have those P terms. So we come up with the P terms, and then we start doing the mass balances. But if you remember the first slide, the water leaves the control volume and it goes out here into what I always like to call the magical treatment device. That reconditions the water into a better water quality. So we have Q, the flow rate and the concentration come in, and then you treat it, and then it goes out. Same that came in typically and has a C out. So where do you get these treatment efficiency terms? That's what you get from your suppliers who are providing equipment, or from practical experience, or from your own farm. Okay. So then, let's see, this is the way I look at it. What is the concentration? You get this magical treatment device. What is the concentration leaving? So again, it's another equation, right? But you have your Cn, like oxygen. Water in the tank was 5 milligrams per liter, okay? And so we're going to run through some kind of a stripping device or oxygen enriched device. And so we'll have the Cn and then C-best. What's C-best? C-best is the absolute fundamental best that that device could do if it was 100% efficient. Okay? So, for example, class, right? If I have an ammonia removal device, what's the best it could do? Remember the plenary session? They said good morning. They're going to say good morning. Good morning. So what's the best, ammonia removal device could do? Zero. Right. So there you go. Right. And so the trick question is carbon dioxide. What's the best that could do? Class user says 0, and I say, well, no, it's more. It's like a half milligram per liter. That's a little trick. Oxygen is a little tricky because if you looked at the second half of the presentation, which I don't have time to do, C-best for atmospheric conditions is going to be, 8, 9, 10, 11, depending on the temperature. And with hydraulic retention tanks we're using, you're not going to really pick up that much between C-best and what comes in C-out. And so that will result in a really, really, really high flow rate, okay? Say compared to carbon dioxide removal or ammonia removal. And so fast forward to this question, well, how do you deal with that? Well, in this equation, you can see the only way you could deal with that would be to address C-best. So if I'm using atmospheric air, C-best is about 10, 9, 10, 8, 9, 10. But if I use pure oxygen, right, it would be 5 times that number. Oxygen is like 20% in the air, 20% in the water, it's 5. So if you actually get up to like 5 times, what the atmospheric condition is. And of course, then that will reduce your required flow rate by a factor of that, or 3, or 2, or something like that. Okay. So I fast forward on that. And keep track of time. So we got 10 minutes and 24 seconds to my 5-minute cutoff. I said I can do this for 3 hours. So there's our production terms. Bert went over that. P term for oxygen, CO2. This is what I like to say. The only number we know exactly in aquacultural engineering is the P term CO2 because it's 1.375 times CO. And you go, wait a minute, well, this is the stoichiometry. CO2 is molecular weight of 44, and molecular number O2 is 32. So you take 44 and you divide by 32, and you get 1.375. The problem there is, well, what was the oxygen? So that could just be way all over the place. So I think some of us think like this is like the best, like, you know, so the fish just metabolically are about 0.25, and the nitrifiers, that's accurate, it's about 0.12 if you start with geometry. And then you got the heterotrophs in there, and so I use 0.13, you could add it up to 0.5. It's kind of easy number to remember, but no one does that. So when I design, I use 1. You can't have not enough oxygen. Okay, and so I think those in the room might say the best I've ever seen is like 0.7 maybe. Bert, what's the best you've ever seen?
0.6, I think.
0.6, okay, so they're at 0.6, because they're Germans and they do things better. Okay, but I design around 1. No one complains if you have too much, right? But you never want to be short. Okay, 0.5 is like the absolute. That's a number you can use with your staff and say, well, we used 0.9 last week, and so it makes us room for improvement. I've been as bad as like 1.8 at times in my career, so that's not good. Okay, so we'll skip those. Valueless fish. There's the ammonia. I always like this ammonia production. So a rule of thumb that many people use for the protection of tan is 3%. Freshwater Institute, Brian Message is 3%. Well, how do you get 3%? Well, the 0.092, you can see that long equation, a whole bunch of soft numbers, I would call them. And protein content in most feeds is say 35%. So what's 9% of 35? It's like about 3, right? So that's where that rule of thumb comes. But that's a really good rule of thumb. Just 3% of your feeding rate, and you'll be fine. Or if you're feeding a really high protein feed, you know, like for fingerlings, it might be 55%. You might want to use this formula. Okay. How I lose fish? The next part. So yeah, I got 7 minutes till my 5-minute cut off. So after you have done the Q times C plus P equals Q times C, then we have to start predicting fish growth in order to come up with this maximum feeding rate. And so the nice thing that engineers like is that, you know, here's time and here's weight or length. And of course, length, weight is cubically related, you know, to length. But length, it's straight. It's so nice. You know? They just keep growing, you know, 3 centimeters a month or 1 centimeter a month. So you have to get about a couple centimeters. That holds true. And that's really, really convenient in terms of when you're trying to say design stages. You know? You can have the all in and the all out, you know, but that's kind of really, really inefficient use of the space unless you use the burp technique where you kind of move them along, which works really well. But we still need to know, you know, how that fish is growing. So they grow linearly at the same time. It's all the same. So you can use that very nicely to stage your system. So for example, if you had a growth period of 30 weeks, you know, from stocking to harvest, well, we could have 3 stages. So that would be 10 weeks per stage, or it could be 5 weeks, and 10 weeks, and 15 weeks. Because they're going to use up 30 weeks, you know, go from the beginning to the end. And then you can use that fact to design your components and your tanks, which I think Ted talks about. Tanks? Yeah, so I'm sure you've probably used that. Okay. So there's the formulas for predicting growth, where we have growth in inches per month or centimeters per month, and it's this temperature that you're using for your fish and some base temperature of which the fish just kind of don't grow. They're okay, they just don't grow. You know, they're all cold-blooded animals chilling down as they're growing. And then there's so many temperature units that are needed to create that inch per month, and those are the numbers. So then you can predict, you know, how fast the fish will grow on a daily basis, which is what I use, then to calculate feeding rate. The other thing, the last thing you need to know there is, you know, what is the condition factor. So I think, this is me, right? I think the condition factor is the most important thing that you can take, you know, as the animal